Hey, okay, welcome everybody again. We're getting started here on what is this? Week 2, day 1. Had a holiday, 4th of July, so now we have only two lectures. And I'll start this chapter, which is number 21, right? Yeah, number 21. And so this is our 4th chapter, and we're leading in towards getting close to the exam. So I wanted to throw out a fair warning out there. And so your exam is next Monday. So that's actually 6 days away, so no reason to panic quite yet, but do need to stay on top of your work. And we only have 2 lectures and 2 chapters this week, and so maybe that's good news, given that you'll want to spend that time making this stuff digest. Because this next chapter, the one we're going to do today, I will tell you some good news here. I think it's one of the easier chapters. It's maybe not as easy as the one we just did, which was 20 and Ohm's Law, but it ties together with that. And so it's about that same level. And so I know you guys were hit really hard at the beginning. That first chapter, 18, was a doozy. Even 19 was pretty challenging. But I hope you found 20 a little more straightforward and a little easier. And 21 is going to be that same thing. We're just going to take what we learned in 20 and extend it. And that's why I call it, I like to summarize it this way. We're not going to do any new physics. There's no new physical principle. But we are going to take the stuff we've learned in the past chapters and put them together. So if there's anything hard, it's that. It's the deductive reasoning that's saying, okay, I got to put all these pieces together. I got to put chapter 19 together with chapter 20 and figure out all the pieces. So that might be the challenging part, and that's what I'm going to hopefully help you lead through. Now, I will say with a little bit of caution that then the next chapter starts with magnetism, and so tomorrow's a real long chapter and a doozy of a chapter, and so that one will little forewarning there and get that one out there. So if you can work any way ahead and have that time free, it would be great to get these done, because you're probably going to want then the 5 days between tomorrow's lecture and the exam to let those things on magnetism sink in. It's our first chapter on magnetism, and magnetism is just naturally a little harder, but it's also the first chapter, and so just like our first chapter on electricity is a little harder. Okay, well, with that, I better get started here right away, and I thought I would begin with this explanation that I was saying. 3 things that I would like you to keep in mind. We've already learned them, but they're worth repeating, but these are the 3 main principles that I would say, if you can keep these 3 in your mind, they can explain all the steps we're going to learn here today, okay? And these are the 3. The first one is Ohm's Law. And so Ohm's Law says that V, voltage, is equal to current times resistance. Of course, we also wrote it in the other patterns, but let me write it this pattern, because you're going to see it in this form mostly today. Well, no, I'm going to put the other form too, because you'll see a lot of this too. And so current is voltage divided by resistance. So those are the 2 forms you'll see a lot here. Now, the other 2 principles are conservation of charge, and the other one is the conservation of energy. And of course, conservation of energy goes back to last semester, but conservation of charge is what we saw in chapter 18. And that just means that we have a certain number of electrons, or lack thereof electrons, and we don't create any extra charge. And so in other words, we've got to explain where they came from. Here's what I mean by that. If I were to draw a wire, and so let's say I had a wire and I label it with current I. Let me just say I1. And so this current is flowing along. And the analogy I was trying to give you in the past chapter is, then if there is, and I don't know if you want to call this a node, a little more formal word, your author uses the word junction. But if you hit a junction, then some of the current is going to go in one direction, and some of the current is going to go in the other direction. But because of the principle of conservation of charge, we know that whatever goes into the node must equal what comes out of the node. And here's where our analogy of water flowing in a pipe or water flowing in a river becomes very useful. Because you know that if this river was flowing maybe 1,000 gallons a second going down this river, and then they hit a divide, well, maybe 700 gallons a minute go one direction, which means 300 must go the other way, because you're not going to get more water. You're not going to just create more water, and you're not going to lose any water. There's not like there's a sink underneath and drains out of the river. And so this is what I mean here by step number 2 here, this conservation of charge. This conservation of charge says every time I see a node, sometimes I'll even call this a current divider, I will say that these two currents that now separated out equal what's going in. Now, we might write it a little different. Maybe I'll write it like, to give us a little more of our circuit diagram, you might remember this little symbol for the battery, and so maybe I'll put a little V here, okay? And then I'll put a little wire, so then I'll say current, and I'll call it number 1. And then maybe it goes somewhere. Well, let me pause right there, because right now, unless there was a node somewhere, I know this. I know that the current up here is I1. That means over here it must be also I1, right? Because again, if the river doesn't have any nodes, if it's 1,000 gallons a minute going through this river and the river turns or something, it's still 1,000 gallons over here. There's no water going in, there's no water coming out. So this principle of conservation of charge is going to be a powerful tool here. It's going to tell us that if you look at a circuit something like this, you know that the current coming into the battery is I1. It's the same that comes out of the battery. It's the same that makes this right-hand turn and goes across the battery. So this is what I was trying to indicate here by, we're going to use this thinking a lot. We're going to use this principle of conservation of charge. Now, maybe then later on it comes someplace and it goes through, if I can use, again, some more of our circuit diagram stuff, and so maybe I'll call this a resistor. And let's call it resistor number 1. And I would say, again, last chapter, that's what we did. We worked with resistors, but we only had one at a time. Now we're going to put a bunch in there. So we might have a bunch of resistors and a bunch of batteries and even a capacitor or two. And so this is the part I was saying that this chapter is good news and bad news. The good news is we're not going to see anything new. We already did capacitors. We already did resistors. We already did batteries. We already did conservation of energy. We already did conservation of charge. We already did Ohm's law. But if we put all those together, we can now do a bunch of circuits and figure out what's going on in our electronics here. Now, I didn't finish here, so let me continue on and say I might have something that looks like this, okay? And so I hope you're seeing here that this current number 1 kind of splits. And now that I labeled it, I'm going to go back just a step, because I find it a little bit easier to solve the problems to try to use the same symbols for the currents. So if I'm calling this current number 1, and I realize then it's going to split right here at the node, so maybe I'll call this resistor 2 so I can match it with current 2. And so I don't have a resistor 1 is kind of what I'm getting at. I'm just trying to say that now current 1, current 2 goes with resistor 2. And I find that a little easier to keep track in my mind. Unfortunately, it's not quite that simple. But what I'm trying to then indicate here is this is a node. And this node, again, trying to illustrate my first principle here, this conservation of charge, would tell me that my first piece of information here is that current 1 is equal to current 2 plus current 3. And so we refer to this as the node rule or the junction rule. The first one to give us help on this was a guy named Kirchhoff. So we call this Kirchhoff's node rule or Kirchhoff's junction rule. Not worrying too much about the name or whether we call it a node or a junction or a Kirchhoff or conservation of charge. Hopefully you see the principle. That's most important to me, is that you see the principle of conservation of charge. That gives us this mathematical relationship. Now, to keep with my symbolism, then I'm going to call this, say, resistor number 3. And then I'm also going to say that, notice then, as current number 3 separated off of this node, it looks like it makes a right-hand turn, and it would still be current number 3. In other words, we're always going to have the same amount of current until we hit a node. There's a chance for more current to come in or some current to go out. But again, like a river that's flowing, you have the same amount of water in that river until you hit another river or a creek that flows into it or splits and comes off of it. Okay? And so that's our first major principle. Now, if I just kind of make this maybe a little more complicated, call this resistor number 4. You might at first even refer to this as current number 4. But again, hopefully you'll see right away, as I was saying, since this is a straight line shot from resistor 2 to resistor 4, they've got to be the same current. There is no place for current to come in or current to go out. So this is kind of a waste of notation and intellectual work. So I'll just say I2 then is also the current in number 4. And that's the part that I was saying. I like to start my labeling so they match, but they're going to fall apart at some point. All right. So this would be, again, I'll call this my first complexed circuit. Something a little bit from a step up from what we did last chapter. In this case, I have 1 battery and 3 resistors. Now, with that all said, I think I covered this pretty good, the principle of the conservation of charge and how we're going to be able to look at this and know the mathematical connection between the currents. I'll say it again. I know that both resistors 2 and 4 have the same current. And I know all the current in this, what we call branch of the circuit, is number 3, and all the current in this branch is number 1, and they meet up at this node, and so number 1 has to equal 2 and 3. Now, if you study this node, nothing new information comes out. You can kind of see that coming down here is current 2, and coming around this loop is number 3. So here we have number 2 coming in with number 3. They combine and make this current right here, but we've already decided that's current number 1 because it's all part of this branch. So we just get current number 1. And so again, we can say what goes in equals what goes out, but you can see that that's not a new piece of information. Okay. And so again, maybe one of the harder things about this chapter is when we start writing out the information we know, make sure we don't kind of what I call double count. We have an equation, and we might think we have 2 equations up here. We clearly have 3 unknowns. And so if we have a tough problem, we have 3 equations need to go with our 3 unknowns. But the truth is they need to be 3 what we call independent equations. And so if there's anything I should emphasize is you could get real careless and just say, oh, I've got 2 equations already. I only need 1 more. No, you really don't have 2 equations here. you still just have one equation, because that second equation is nothing more than the first one repeated. And so that could be a challenge, making sure students get independent information. All right, now the second major principle right here, conservation of energy. And again, I'll use water and potential energy, gravitational potential energy, like we'll do electrical energy as my analogy. And we like to say this, okay? We like to say, and maybe again, I'll just use the analogy of a river. And so here's this water coming in at, I call it the main part of the river, current number 1, and it splits. Okay, so let's say that it splits, and right here it goes over a waterfall. It goes downhill. It loses gravitational potential energy. Now in our case, we would say this is electrical potential energy. So let me call this V3. What I mean by that is this is the amount of voltage change because of the resistance. Now, if I wanted to then incorporate Ohm's law with this statement, I guess I would say that this must be equal to current number 3 times resistor number 3. Okay? But there is a change in energy. Now remember what voltage is. So let's go back 2 chapters. Chapter 19, voltage is the amount of energy per unit charge. So when I say the voltage or the change in the voltage, I'm really saying a change in electrical energy. And so that's why I'm doing the analogy of a waterfall. The water went over this waterfall. The water now has lost a certain amount of gravitational potential energy. And so we have gone downhill. But let's look at the other direction here. Remember, the water split here at I1, and some of it goes this path. And in this case, you might say it goes over 2 smaller waterfalls, or 2 cascades, right? It goes through 2 resistors. It loses energy twice. Maybe we would call it the voltage at number 2 and the voltage at number 4. But eventually the water comes together. So wouldn't you know that when it comes together, they would each go down the same total amount? Because they meet. You never have a river meeting where water goes under the other one, right? They meet up at that same level. And of course, if there was some way that it was under, what would happen is more water would flow over here until this filled up and it matched. And that's exactly what will happen with our electronics. What happens with our electronics is if you go one path, there will be a change in energy. And if you go the other path, there will be the same amount of change. Or let me put it another way, the way your author puts it, the way Kirchhoff put it, and the way we'll probably say it the most. They're saying if you did a loop, let's say you were going on a hike next to the river. Let's start right here where the 2 rivers come together. You start here and you decide to hike along this path. And you hike along this path and you get, of course, to this waterfall, and so maybe you got to go up some switchbacks. You have to go up a certain height. Then you go across the trail and you go, hey, let's return back this other path. And so you follow downstream and you go down the first cascade and down the other cascade and you get back where you started. You're at the same height where you started. See, this is where you parked your car. You drove up to the trailhead, you parked your car, and what you know is you went uphill and then you went downhill. And you know that you went uphill the same amount you went downhill, right? Nobody gets back to their car after a hike and they're like 10 meters above their car. You're at the same spot as your car. You're not underneath your car. You're not above your car. The change in potential energy is exactly the same when you go around a full loop. Sometimes you go uphill, sometimes you go downhill, but the total change is 0. We're going to take advantage of that. This is what I'm saying is this principle of conservation of energy. This is what's saying is if you go all the way around a loop, sometimes you will go uphill, sometimes you will go downhill. If you add together all of your uphills and all of your downhills, you're going to get a total change of 0. Exactly. You're going to get right back where you started. So to help us think about this, let's label a few points here. Why don't we do this? Why don't I call this point A, this point B, this point C, this point D, this point E, and this point F. And if I were to ask you how many loops are possible here, do you see that there's 3 of them? Do you see that what we could do is the loop I was first explaining, this one, which let me call that the right loop. But we could also do this loop, the left loop. But we could also do the big loop. And so either of those loops, if you were to add up all the changes in voltages, you would get 0. And so this is what I'm going to do for the rest of the lecture. I am going to apply the conservation of energy, saying if I add up all the voltage changes around a loop, any loop, every loop, I will get 0. If I look at all the nodes and all the junctions, the conservation of charge, I know that all the current going into a junction equals all the current going out of a junction. I also know that for any branch, the current's the same all the way through that branch. And that is the fundamentals of this chapter. This is a good time to say physics is about knowing how to apply a few powerful fundamental concepts to explain a universal phenomenon. The rest of this will just be deductive reasoning here. All right, so why don't I do each of these loops? I'm going to go ahead and start with the one I did first, the right loop. So why don't I call this loop, and let's see, where should we start? I imagined parking the car right here at E, and then going to F, and then D, and then C, and then E. So, all right, I'll say, let's look at loop E, F, D, C. All right, so I am going to then just move along on this imaginary hike. If you like, you could think of yourself actually in the wire, kind of moving along. Sometimes I like to imagine myself, I'm hiking actually in the creek. And so I'm splash, 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 you know, or I'm inside. Sometimes I like to imagine myself that I'm in that animated cartoon. Do you ever watch The Magic School Bus? Oh yeah, yeah, okay. I love The Magic School Bus. And so they go on these magical field trips, and there is even one exactly like this, where the school bus, they shrink down and they get inside the wire and they go throughout the cities, and then they end up popping out back at the school at the end. And so imagine yourself in this wire, all right, and you're moving along here, and everywhere there's a change of energy, we just have to add it up, because the whole idea is the total change in energy would have to be 0 if you go around a full loop. So, in other words, using Ohm's law, anywhere there's some resistance and some current, there's going to be a change. There's also going to be a change anywhere you have a battery. Remember the chemicals that are in the battery. I guess there would also be a change where there's a capacitor, but I better hold that off. That's later in the chapter. That'll be after the break in the lecture. Capacitors are a little harder, so we'll hold off on capacitors. Let's just build up. So right now we just have resistors and batteries and say, okay, what would I do? So if I can imagine starting at E and going to F, I have a wire, and this is the part I was saying, most of the resistance is really in these resistors, in the light bulb itself. And so when we connect things together with a wire, as we were talking about in the last chapter, technically there is a little bit of resistance, but it's small. Remember, these are made out of copper, and so we got the resistivity of the copper times the length of the copper divided by the area of the wire, and this is a pretty fat wire. It's not very long, and it's made out of good conducting copper. So if you say all that, it's pretty much implied that the resistance is 0, so whatever current I have doesn't really matter. I'm going to get zero change in energy. And so from E to F, no change. So I won't even bother to write anything down. But I do want you to know I thought about it. I went from E to F, no change in energy. The real change happens right here at resistor number 2. And so when I go from F to D, there would be a change in voltage. I called it number 3, and I'm going to write it as current 3 times resistance 3. Okay? And so there's my first change. Now, here's something you'll have to ask yourself. It's a change, but is it an increase or a decrease? Are you going uphill or are you going downhill? Now, here's where you have to be careful with this little analogy, because there's two things moving here. There's you walking the trail, and then there's the water moving. Don't mix those two. So the water is the current. You are making your marks. Aren't you going uphill? How do I know I'm going uphill? Because water always goes downhill. So which way is the current labeled on here? This way. So the current goes this way. So if I find myself walking this way, if you imagine yourself in a creek and the water is flowing from your right to your left, and you're walking against the flow, you know you're walking uphill. The water always goes downhill. Okay? Now, this is where it gets kind of interesting. Some problems we don't know which way the current's supposed to flow. But here's the best part. Pick a direction. Solve the problem. And if that current comes out to be negative, that just tells you the current was actually going the other way. So we don't have to really even know what direction it flows. We just have to label a direction. More on that as we get into some examples here, but what I want you to see here is I'm going to put a plus. The change in voltage using Ohm's law is current times resistance, and it's a plus because I'm going uphill. How do I know I'm going uphill? Because I'm going against the current. All right, same thinking. Let's go from D to C. Again, I would say that's just a regular wire. There's no resistance there. There's no change in voltage. That's just like the E to F. Let's keep going. Now, to finish my loop, I'm going to go from C to E, and then notice there would be two changes in voltages because there's two resistors. So this would be a current 2 times a resistor 2, and the other one would be current 2 times resistor 4. And I deliberately did not put a plus or a minus because I'm going to ask you, now, would this change in potential be a plus or a minus? How would you know? Well, again, ask yourself, which way are you going compared to the current? Right? We know that the water current always goes downhill. So the electrical current, the potential, so for electrical current, the current always goes down to lower potentials. And so if you'll see here, I'm actually going with the current. So if you're walking in a creek, splash, 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 and you're walking with the current, you're going downhill. So these are decreases. So minus, minus. And then we get back where we started. And we started this whole conversation by saying, if you go around a full loop, what does all the change in potentials have to be? 0. All right, so I'm going to say it again, and probably a few more times before today's over. I'm just going to keep doing this over and over again. I'm going to look at the conservation of charge and the conservation of energy. What that really means is the current going into a node equals the current coming out, and it also means the change in the potentials have to add up to 0. And if you can do that, you're golden for this chapter. That's this whole idea. Now, this may be obvious. I don't know. I'm going to give it a try. What if I did this loop in reverse? What if I did the same loop starting at E, but this time I go to C, to D, and then to F before I return back? So I go around the loop, but I go in a different direction. what would my equation become? So again, parking my car right here at E. I'm going to get on the trail and I am going to go from E to C. And in that case, there are 2 changes, right? So I would write down the first change as current number 2 times resistor 4. And the other one would be current number 2 times resistor 2. I guess my question now, would it be a plus or a minus? Plus. It's a plus. Good. You guys are seeing it. So I'm going, because I'm going uphill, right? I'm going against the current. And so it's just the opposite of what I had before. I'm just doing the same trail, but I'm going the other direction. And then, of course, I would get from C to D, and as we said earlier, no changes there. So then I would go D to F, and then D to F would have the change of voltage as current 3 times resistor 3. And that's the change. And then, of course, here's my question, plus or minus? Minus, very good, because I'm going with the current. Now I get back where I started, and that is 0. And so notice I picked a loop. Notice that when I added up all the voltages, I set them equal to 0. Notice it didn't matter which way I went around the loop. The key is you just have to go around a loop. And you can go clockwise or counterclockwise. Doesn't really matter. But also, did you notice that that's really the same equation? So if I'm trying to solve this for, let's say, a given problem, let's say we know the voltage in the battery and we know the resistors, and so we're asked to find how much current number 1, 2, and 3. We have 3 unknowns. So to solve for 3 unknowns, we need 3 equations, our system of equations. And so just like back here, I had to say, well, this doesn't count. This is not new information. I would say the same thing here. This doesn't count as a new equation. This one does. So I have 2 equations. But right here, I'd say this, not useful. All right, so know this, that if you do a loop clockwise, don't do it counterclockwise and think you got more information. It's either clockwise or counterclockwise, your choice, but don't do it both because that's not a new piece of information. And if you try to solve equations where you have 3 unknowns, but you don't have 3 independent equations, you get to one of these things that you probably did many times in your algebra class. You work real hard, you go through all the math, and at the very end you get 5 equals 5. True, because you didn't do anything wrong. It just didn't help you solve the problem. And so you don't have independent equations. And that's what will happen if you don't have independent equations. Okay, so like I said, true, not useful though, once we've done this direction. So again, go counterclockwise or clockwise, your choice, but only one direction. All right. Hey, let's try another loop then too, because now you can see that we need one more equation. We have an equation here, we have an equation here. Let's try another loop. All right, so I'm going to try loop. And I'm going to do what I'll call the right-hand loop. Let's kind of do the same thinking. Let's not bother, now that we've already learned you don't want to do both clockwise and counterclockwise, but why don't I just imagine I'm doing this loop for my hike, and I'm going to park my car at A, and I'll just go around in a clockwise direction, okay? So we'll go A, B, C, E. So A, B, C to E. So this is going to be my loop. All right, so I'm going to take this loop. Now, here's something new. This is a battery. We already talked about how to calculate the change of energy in a resistor. It's just Ohm's law. How do we get it for a battery? Well, here's the great thing about a battery. A battery is much easier. That is what we mean by the voltage of the battery. The amount of energy comes from the chemical reaction. If I pick up one of these D cells, I know that it is 1.5 volts. End of story. If I have this motorcycle battery, it's 6 volts. End of story. Now, I'll probably ask myself, is it a plus or a minus? But it's 6 volts. There's no current involved. There's no resistance involved. So I don't have any of these IR terms. I just have the V. So I didn't give it a number purposely because I wanted to start off this morning kind of abstract and just say, okay, this is V. So if I go from A to B, I would say that there is a change of voltage of V. That's what we mean by that battery. Just how much is on that battery? Is it 1.5 volt? Is it 6 volts? Is it 7 volts? You know, who knows? Let's see. Do I have this on? Yeah, I've got this on there. I got this set for 6 volts. So it's just 6 volts. Now, how do I know if it's plus or minus? Well, again, that's what the little and big bar mean, right? The big bar, if you remember, means this is a higher energy. So I went from low to high. So I'm going plus. And so I would just write plus. And again, did you notice it didn't have anything to do with the direction of the current? And so I want to emphasize that. Because when I first talked about resistors, I kept asking you, is it a plus or a minus? And the answer to that is we had to compare it to the direction the current was moving. And that's true for resistors, but that is not true for this battery. This battery is its own energy source. This uphill and downhill stuff this is just a pump, if you will. I just give it more energy, okay? Now, don't get me wrong, it would depend on which way you walked around the loop. Okay, so if I had gone this way around the loop, when I got to this battery, I would go from big to small. So then I would put a negative. So there are times I can put a negative. I just had to ask myself, which way did I go around the loop? Right? And that's why I said here, you got to, for this analogy to work well, you need to think of yourself as hiking near the creek. And so you got two things moving. You've got you moving around the hike, and then you've got the water that's flowing in the creek. Okay? And so you're adding this together. So anyways, going this direction, I would have an increase of plus V. And then as we said before, B to C, no change there. C to E, these are the two changes again. I'll write them down. The first one is current 2 times resistor 2, and the other one is current 2 times resistor 4. And you guys already answered it well already, but I'll ask it again. Would they be pluses or would they be minuses? Yeah, they'd be minus. We're going with the current. And we would get to E, and then when we got to E, we'd go from E back to A. That would finish the whole loop. We've got a complete loop, and set that equal to 0. Now, I said I wasn't going to go the other direction, but let me go ahead and go the other direction just to show you. Let's go A to E to C to B. And if I went from A to E, I would then go uphill against those two resistors. So this would be current 2 resistor 2 and current 2 resistor 4, and both would be a plus. And then I would go up to C, and then I would get to this battery, and this is what I wanted you to see. As we go through this battery, I would go from the bigger bar to the smaller bar, so that would be a minus AV, and I would complete the loop, and I would get 0. And again, notice that this equation is really the same as that equation. It's just this equation multiplied by a -1, so it's not any new information. So that's kind of useless. And so I'll say it again. Either go clockwise or counterclockwise, your choice. Don't do both. And I guess technically I'm done, because I would probably have a problem like this, where I would be given the voltage of the battery, I would be given the resistance of the resistors, and I would then not know current 1, 2, and 3. And so I have 3 equations, 3 unknowns. And so I'd put in my values of my resistors, I would put in my values of the voltage, I would get lost in a sea of algebra and solve it. And I will start to do a sea of algebra for you, but not quite yet. I don't think we're ready there yet. I'm just trying to get the principles there of what is our fundamental principle. Now, with all that said, let me also point out that I could do the big loop. Remember we said earlier that there are really 3 loops here? However, what I want you to see is once I do the two small loops, the big loop is not new information. The big loop is what you would get if you added this equation to this equation. If you add the right loop together with the left loop, you get the big loop. And that's how I ask the students to think about it. I say, look, one of the challenges you will have is getting independent equations. Because again, we have 3 unknowns and we need 3 equations. So how do I know I have independent equations? And the best answer I can give is just do the small loops. Always do the small loops. Because if you do the big loops, they are nothing more than the combination of the smaller ones. And you're not getting any new information. However, sometimes doing the bigger one is useful. So I would say if you do the big one, then you need to not do one of the smaller ones. Because the big one minus a left one is equal to the right loop. All right, so you just can't do 3 loops. So again, if somebody stood back and said, hey, I have 3 unknowns, I need 3 equations, and they do the left loop, the right loop, and the big loop, and they go all this algebra, they're going to finish the algebra at the end of hours of work and got 5 equals 5. And go, oh, okay. 5 equals 5. And you're right, you didn't do anything wrong. You just didn't do it independently, so it didn't help you solve the problem. And so that's a little warning in there. All right, so like I said, I'll do the big loop and see what we get. And so I'll do this big loop, and I'll just go, just to be different, I'll go counterclockwise this time. So let me go to A to E to F to D to C to B. So what did I say that was? A to E to F to D to C to B. Let me add up all the voltages. Now it's kind of boring from A to E and also boring from E to F. Finally, F to D is interesting. So F to D would be this I3, R3. And since we're going against the currents with a resistor, that would be a plus. And then the D to the C would be boring, nothing to write there. C to B, kind of boring, nothing to write there. B to A, again, there is a change of voltage. It's a battery. Remember, batteries have nothing to do with Ohm's law and current. It's V, that's it. And then is it plus or minus? Well, it depends. Which way did you go? Well, I went from the big to the little, so it's a minus. So this would be a minus AV equals 0. Now, this is a good example where this big loop mathematically is probably easier than these two. So I would be tempted to say, why don't we use the big loop and not one of the small ones? Your choice, which one not to use. And to be quite honest, this one looks like the harder one, so I would throw that out. So if I was solving this mathematically, I would probably use this loop, not this loop, and that loop. But notice I can only use 2 of the loops. And so, again, my suggestion is look at the number of loops. If you get lost at all, just do small loops. Sadly, though, that might be harder mathematics. Okay, but definitely smaller loops would be knowing they're all independent. However, if you decide to do a big loop, make sure you don't do a small loop. Or here's the easy answer. Only do the number of loops that you have of small ones. We have 2 small loops. So make sure I only use 2 equations involving loops. I would not want to use all 3 equations to solve this. I could not. All right, so maybe I'll throw this name out again. And so these loop rules are Kirchhoff's second rule. Okay? And so these are called Kirchhoff's laws. He's using this principle of conservation of energy and conservation of charge. Now, fortunately, there are some times where things can come out pretty simple. Simpler than you might have first expected. And I don't know if you saw it here, But the easiest one was this big loop. Right? This just was basically saying that the current goes through here and then it independently goes through here and here. Do you remember last chapter we used those words series and parallel for the capacitors? Let's use those words again. What do we mean by series? What do we mean by parallel? Well, series means you flow from one into another. There's no other place to go. Using the term of a node, we would say something like this. These two resistors, 2 and 4, are in series. They go from one to another. There's no other place for the current to go. It just goes from number 2 right into number 4. So we call that a series. And so I would say those are series. Now, in your mind, if you group that together for just a second, okay, so call this a branch. See how this branch and this branch, though, are parallel? Maybe this is a good point or a good time to grab a picture from your textbook. Because your author actually kind of starts here in a special case, and I decided maybe I would jump in to kind of the more general information and then focus in on special cases. And the special cases is what happens when they're in series or in parallel. We can make things even easier on ourselves if we get so lucky. And so your author is saying anytime you have one leading to another, leading to another, leading to another, that's called series. There's no place for the water or the current to branch off. And so this little piece right here, R2 to R4, those are in series. But then something that looks like this, where the current comes in and then it divides and it can go this way and then it can go this way and then it can go this way and then it can go that way. Those are parallel paths. Those are like 4 lanes on the freeway we were talking about last time. If you got on the freeway from here and you were going to Carp, you don't go in every lane. You don't have to go down one lane and go down the other lane. You just get in one lane or the other. All the lanes go down there. And some of the current goes in lane 1, some of it goes in lane 2, some of it goes in lane 3, and some of it goes in lane 4. And everything that goes in lane 4 never goes through lane number 1. Those are parallel paths. They're moving down in the same position. And they're all going to get to this position. And so, like I said, sometimes that's really, really nice. And here's why. Here's what your author is saying. If you ever have them in series like this, and so here he's showing a battery and he says, look, it goes from R1 to R2 to R3. You can make your life easier if you pause for a moment and realize a nice mathematical pattern, that those 3 that are in series can be simplified. And so he's saying there is an equivalent resistance. Remember we did that with the capacitors? We said there was an equivalent capacitance. If our capacitors were hooked in series, we can take those 2 and we can write what it's equivalent to. We're going to play that same game. Let me turn that off for a second and come back to my equation. Right here is where you see it for resistor 2 and resistor 4. 2 and 4 can be simplified. Watch. Let me take this equation. Let me take this equation, and since I am not going to be using this one under here, let me erase this one. Watch what happens. I can take V, and then these 2 I can move to the other side, so they become a plus I2 R2 and I2 R4. And this is where the math comes in. Notice, because they're in series, they had the same current, so you can factor that out, I2, and then you just have the sum of the 2 resistors, which is what you would have done if there was just one resistor there. Had there just been one resistor, you would have called it the equivalent resistance. You would have said, oh, that's just some resistor in series. And so we could have made this problem a little easier on ourselves than the general principle that I started with. So if you can, and I want to emphasize, if you can, you can't always, but if you can, look for things that are in series. Because if they are in series, you can take those two and combine them together, and this is mathematically how you will do that. Let me put a box around it, but if you ever see some resistors that are in series, just know that you add them. Now, I only showed that with 2, but you can see your author did that with 3. And so his general rule is this: resistors in series, you just take the first one, and then the second one, and then the third one, and however many you have, and add them together, and that's your equivalent resistance. And then you're going to have an easier circuit. And now you might not have so much mathematics to do, and that you'll appreciate. So like I said, there are some special cases. So even though I started this by giving you kind of the general overall principles of conservation of energy and conservation of charge and 3 equations and 3 unknowns, we could actually just do this by putting it in its equivalent resistance and solving it, and we're done. At least for that one piece of the equation where it's current number 2. And so that's very powerful. In fact, let me do this. Let me put then over here what I will call the equivalent resistance. And I'm going to put R series right here by saying I'm going to think of number 2 and number 4 as one resistor. And so now I have a circuit that is a little easier. And like we did with the capacitors, you might remember some of these hard problems we did, is we said, okay, now if you look at the equivalent, then maybe there is another equivalent step you can take, right? Maybe there's the equivalent of the equivalents. And so notice something neat about this. Maybe you kind of see it. Keep in mind the very first equation we did. Current 1 equals 2 plus 3. Maybe I should label it in my equivalent here. So this is saying, here's current 1. It branches off and becomes over here current 2, and branches off this way and becomes current number 3. Okay. But if you did a loop right here, you would say V minus I2 R in series. And if you, n equals 0, that would complete the loop. And if you do the big loop, which I already did right here, I would have V equals I3 R3. Now watch what happens if I solve this for current number 3. I get V over R3. Watch what happens if I solve this one for I number 2. So I'll move this over to here. So here's I number 2. That would equal to V over R series. And let me just ask this question. These two I would call parallel. Now I think parallel is a little bit harder to notice than series. Series, remember I said one flows right into the other. There's no other node. So if I can draw a straight line from the end of the first one into the second one right here, that's series. Okay, right into it. Parallel means that if I get here, I can go this path and get exactly the same place if I went the other path. and I don't hit anything in between. So do I have that? So let's say I start right here, which we call this point C, and I'm going to regroup my thinking at point E. So if I went from point C to E, I would go through this resistor. But if I went from C to E through resistor number 3, I would go this way. Notice that as I go each path, I get back where I started. Not back where I started. I start at the same place, I finish at the same place. And I only went through each of those resistors. There weren't other resistors. There wasn't a node flaring off. There wasn't something to get in the way. There was just either path. That's parallel. You can go this path or you can go that path. I'll say it again. It's like going to carp on the freeway. You can get on the fast lane or you can get in the slow lane. You can get in those lanes and just go. There's nothing else in between. Well, I guess technically there is a bunch of off-ramps and on-ramps between here and carp. But if there weren't any on-ramps between here and carp, we could get in one lane, we can get the other, we could just keep going and we meet up. Okay? If you ever see something like that, and that's going to be the challenge, getting you to recognize when they're in parallel, but of course that's why your author introduced you to capacitors first. But if you ever have something like that, I'm trying to say that you could have an equivalent, and we'll call it the equivalent of R parallel. And again, that could be a very powerful tool, because as you saw, when I started this problem, it looked kind of hard, it looked kind of long, it looked like I had a lot of equations and I had to work all this stuff out. But if I notice some patterns here, I can simplify things. And as you saw, I already took what was 3 resistors and reduced it down to 2 resistors. And I'm going to say you can do the same thing here. You can reduce it down to 1 resistor, because just like there's a mathematical equation for resistors in series, which we've already seen, there is a nice mathematical equation for resistors that are in parallel. And so if you ever recognize they're in parallel, use this equation. And I'll derive it here, and it really comes from this right here. Remember, current 1 equals 2 plus 3. So if I come back and write a loop for this, so here's V, here would be current number 1. There is no splitting anymore when I've got the equivalent of the equivalent. So remember, this is the real circuit. So I like to call this the equivalent circuit. And so I like to call this the equivalent of the equivalents. And so I would do a loop, and I would go V, and I would go I1 times I parallel, and I'd be going with the current, so it would be a minus, and I'd put a 0. So there's my principle of conservation of energy. And if you look at this, this says then that I1 would equal to be V over R parallel. And so if you take that equation, and that equation, and you put them into this equation, you get V over RP. Here you get V over RS. And here you get V over R3. Notice every term has a V in the numerator, so I can cancel it off. And that means the resistance in parallel, I'll call it the equivalent resistance in parallel, would be adding the reciprocals. And so let me encourage you to remember this equation and this equation. So if we ever see a complicated circuit and they're in series, we'll just add them together. If we ever see a complicated circuit and they're in parallel, well, we'll have to do the reciprocal sum. But we can eventually then figure out what the overall equivalent resistance is. Now, maybe I should put it the way your author has it, because I put a series here because I had 2 in series that I got the equivalent. But your author says if you ever see something like this, that you have a bunch of resistors in parallel, and even though I showed only 2 of them, I think your author had 4 of them in parallel. But he says you could be 4 or 5 or 6 or 7, however many. You would just do the reciprocal sum. And so that's why I like to do the dot, dot, dot. I think he had the 4th one, but dot, dot, dot. All right. So again, these series and parallel can be nice ways of reducing things down. Well, I've said a lot, and so this I think will be a good time to actually do a first example. Why don't we go and look at example number 2, or problem number 2 here in the book. Oh, I should have wrote down what page this is. Let's see, I'm on 907. See if I can remember 907 and then see the problems. Looks like they're right about here. Those are the conceptual ones. Okay. All right. So about a 947. All right, now let me just read this one and say, okay, here is some of the easier problems you're ever going to get when they're series or parallel. And so number 2 says, what is the resistance of, and they do a 100 ohm and a 2.5 kilo ohm, so that's 2005 ohm, and a 4,000, so 4 kilo ohm resistor connected in series and in parallel. Okay. Now, I'll do this example with a small change. They gave us 3 resistors, but so that I can test this with you and also demonstrate how to use some of our lab equipment, let me do this. I'm going to grab some resistors, and I've got 3 of them here. Actually, I got 5 and a bunch more over here. But why don't I grab what's labeled here as resistor F, and I'll just work up from the bottom here. But I'm going to use my ohm meter. And as we get into lab and we play with our little devices, you'll see that I will say you connect it to the little dot that says ohm meter, and you take a reading. So this one says 105.2. So let me take resistor 1 as 105.2. Let me take resistor number 2, so I'll go 1 up. And say, all right, just changing there. This is a 205.7. So 205.7. And let me take resistor number 3. And 751. Grab my calculator, and let me put the little ohm symbol here. And answer A. A says, if you were to hook these 3 up in series, what would be its equivalence? Well, this is the easier one. This is where you just add them together. So I'm going to take my 105.2, my 205.7, and my 751, and I will get 1,062 ohms for the equivalent if I were to hook them in series. And again, maybe to help you understand what we mean by series, let me do this. Let me disconnect my meter. Okay, so meter's gone. And series would look something like this. It would go from the first one into the second, then from the second into the third, and then through the third, and then out here. So to do that, I guess I'll need 2 wires here. I will connect there to there. So starting here, it goes through 1, This wire then connects one directly to 2, right? See, there's no other connection, no other node, nothing in between here. That's a series. Okay, so then I will go through that one, back to here, and then number 3. So the question is, what's the resistance from the beginning of this first one right here to this one here? So I will come over here with my meter and say, all right, so the beginning of the first one to the end of the third one. And I get 1,062. Yay, it worked. Proud of myself. All right. So it does work. Now, let's try B. B says, what would these 3 be if they were in parallel? What are they equivalent to? And by the way, as a side note, you could even see it in the mathematics. Let me stay away from too much of the mathematical proof. But if you ever put them in series, isn't the series always going to be bigger than each of the individual ones because you're adding them together? So series is always bigger than any of the individual ones. So in other words, I like to say it's going to be, in series, they're going to be bigger than even the biggest one. But what about parallel? Parallel will always be smaller than the smallest one. Because again, it doesn't really matter how much resistance you have. If you add another path, the total is easier. It's like adding a lane to a freeway. If our freeway gets congested because it has 2 lanes, you put a 3rd lane there, even if it's a slow lane or a side road, that is less resistance to get to CARB, even if it's not a very good road. You say, well, that's not very much low resistance. Yeah, but at least it helps some. So some of the cars go that way. And so when you start putting resistors in parallel, the overall is going to be less than the lowest one. So my lowest one is 105. So when I put these together, I should expect a number less than 105. All right, so let's see what I get here. And I will first write it and then take advantage of my calculator. As I was showing you with capacitors, it's nice to write this as R1 reciprocal plus R2 reciprocal plus R3 reciprocal. Because when you do that, you are going to get R parallel reciprocal. And so when you just add them together, then you can hit the reciprocal key when you're all done. So when I enter them, I like to enter it this way, 105.2 and hit reciprocal. Got it. Plus 205.7 reciprocal. Plus, what was the other one? 751 reciprocal. And so I'll point it out, you know, there's always a reciprocal key on these nice calculators. My TI-84 has it, I guess 1, 2, 3 from the 4th one down from the top left. Anyways, so find that reciprocal key. Okay, and I like this model because the reciprocal key is not a shift reciprocal key. You know, and I just use it so much, it's nice that I don't have to go shift, shift, shift. But obviously, find it on your calculator, and don't change your calculator just for that. But that's why I like this model. It's not a couple extra keys. Anyway, I've got them added together. So I'm going to hit enter, and then that gives me the reciprocal. So then I hit the reciprocal of that, and I get the equivalent in parallel as 63.7 ohms. And notice, as I said, notice it's less than 105. And so when I hook these 3 up in parallel, I have an easier path than just one of them by itself. Any of them by themselves. It makes sense. All right, let's hook it up though. This will give me a chance to again kind of show you. So here's the meter. So I'm going to put the meter off by itself. And that's what you'll hear me say in lab. Like the best way to use kind of a meter is remembering it's a measuring device. So hook everything else up first and then come over here with your measuring device. Okay, now let me just disconnect all these wires. And maybe before I hook it up, it would be worth seeing kind of a picture of what do I mean when I say hook this up. Okay, well, maybe the picture should look something like this. I've got resistor 1, resistor 2, resistor 3. And as I said, sometimes recognizing them, whether they are in series or parallel, can be the hardest part. But parallel means that if you take a path, you'll meet back up without bumping into anything else or going off on some node or some other direction. So if I imagined coming in right here and I hit this T, I could go this way or I could go this way. And notice that I go through one each, and so each resistor, so these two are in parallel, and then back in, right? They meet up. And so I would say 1 and 2 are in parallel. And 2 and 3 are also in parallel. Notice that I could come down here and then right here split off, and I could go through number 2, or I could go through number 3 and get back to the same place. So when I go to number 3, I go just through that resistor, no other resistors, and there's no other nodes for it to split off of. And so that means 1, 2, and 3 are all in parallel. Which means, of course, I can use this formula, which I've already done, and now I can hook it up and see if it matches. All right, so looking at that picture, I hope you kind of see how one side of every resistor are connected together. So one side, I'll call it this side, are all connected together. So maybe I will connect number 1 to number 2, and then number 2 to number 3. So I needed 2 wires to do that, but hopefully you can see that everything over here on my right is all hooked together. Now, maybe I should say top. So everything on the top is hooked together. Okay, so then I want everything on the bottom hooked together. So I'll get another set of 2 wires and do the bottom. Okay, so take those 2. So it looks like number 3 and number 2 are connected together. Maybe doesn't matter what color, but sometimes mentally just helps to be color coordinated here and make things match. So I did reds up here and blacks down here. Anyways, but now I just connected 1 to 2 and 2 to 3. Okay, so I've got all the ones on the top together, all the ones at the bottom together. So that's a parallel connection. Okay, and then if I took my meter and I hooked it from the top to the bottom, I should get the reading when they're in parallel. So here's my little meter. I'll put it 1 at the top, and it doesn't matter where I plug it in at the top. Every one would be equivalent, and 1 at the bottom. And what do I get? 63.8, and we calculated 63.7. So sure enough, it works. All right. And so that's our series and our parallel. So I'll say it again. If you ever see anything like that, you might want to try to simplify things before you move on, because your author then shows you, let me go back to page 907. So here's his series, and here's what I was just saying. Here's his parallel where he shows 3 of them, and he says, let's just replace that with 1. And so that's the equivalence of those 3. And you can make your circuits a little bit easier. Because here's going to be the grand finale type of problem. It's going to say, hey, take a circuit like this. You have a voltage, and it looks like we've got a resistor, 7 resistors. And a bunch of loops. But is there any way we can make it easier on ourselves so we don't have to write out 7 little equations and 7 different pieces? And the answer is yes. Your author says, stand back and look closely at it, and hopefully you will notice that these 3 are in parallel. Okay? And if you went from here, you could go through this path, or you can go through that path, and you go through just those 2 resistors, and you get right back where you started from, or you can go this path or this path. And so all 3 of those are in parallel. There's another group in parallel with each other, so these two are in parallel with each other. And so your author is saying you can simplify this and replace these three with that equivalent. And you can replace these two with that equivalent. And so now only have a circuit with 4 resistors. That's probably easier to work with. But if you stand back and draw this, you will then notice that this equivalent one, which represents these 3, and this equivalent one, which represents these 2, these go one feeding into the other. These 2 are now series. In other words, once I've done the equivalent, I can do an equivalent of the equivalent. And I can take these 2 and put them together and call it that one right there. And so now I'm down to this circuit, which only has 3 resistors. So this circuit, which I call the equivalent of the equivalent, is down to 3 resistors. And then, look at this, those 2 are in parallel. So I can combine those 2 together and get this. So this is the equivalent of the equivalent of the equivalent. And then finally, I will notice that those 2 are in series. And I'll put those together, and I finally get all the way down to 1 voltage and 1 resistor. And that's just Ohm's law. The current is just V divided by R. And so this one right here, which is the equivalent of the equivalent of the equivalent of the equivalent. Or no, this is the equivalent of the equivalent of the equivalent of the equivalent. Okay? And so that's how we would solve a complex problem like that. We would just kind of put those ones together. All right? So that's this idea. Now, your author says, all right, let's not do anyone quite that hard. I'm not even sure why he gives you something quite that hard in his picture, and he says, let's just do this one together. And then he puts these 2 together and gets the equivalent, and then he puts those 2 together and gets that equivalent, and he solves the circuit using the equivalencies. And I'll do some more of those equivalencies in a second here. But I just wanted to say one more thing, and it'll probably be a good time for our break here, is batteries. Batteries can be interesting. Because at this point in the lecture, I've done something like this. I've said, okay, here's the battery, and I hook it to a resistor, or maybe 2 or 3 resistors. But I brought our batteries out here purposely to say, okay, batteries have some kind of chemical in them. This is our lead acid battery here. And so there's really kind of 2 things going on in the battery. The first one is the chemical reaction, which makes the voltage. But then all those electrons have to move through all this material to come out to the terminals. And that means there's some resistance along the way. And so your author says this. He says, maybe the best way to think about a battery is that inside the battery it's made out of 2 pieces. And so let me come back over here to my diagram and do this. Let me kind of open it up and put a little tiny resistor in here. And I'll put a dotted line here. And I will say here that the voltage at the terminals, and so voltage, again, at the terminals, and so what's called the terminal voltage, is going to be what? Well, let's do our conservation of energy. And he says, and he uses a little script E here. He says, you're going to get a certain voltage from the chemical reaction. Let's call that a script E. His script E looks a little better than mine, but that's probably the best I can do. And so he says there is the energy you get from the chemical reaction itself, and then my Ohm's law again. Remember I said we're going to use this a lot? Oh, I erased it. Remember I said principle number 1, Ohm's law, we're going to lose a little energy just getting the electrons out of the battery. And so what he calls the terminal voltage here is actually the EMF, and so that's the chemical reaction. So he refers to this as an EMF, stands for electromotive force. And then you subtract off a little bit of loss because of Ohm's law. And this then is going to be the actual reading on the terminals. Now, hopefully, one of two things is happening in most batteries. Most batteries, then, this resistance is small, and we ignore it. And I got to admit, that's a little bothering for students at times, because sometimes we ignore it and sometimes we don't. It's like friction. It's always there. Sometimes it's just negligible. And so we're going to say the same thing. There's always a little bit of internal resistance. We just sometimes and often ignore it. And so if the problem dictates we ignore it, it probably means that this resistor, which, if you'll let me use a fancy word, we'll call the load resistor. This is what we actually want to use the battery for. We're saying we're going to hook something up to this battery. We're going to hook up a light bulb. We want to run it. That's our load. And if the resistance of that light bulb is a lot more than the internal resistance of the battery, we'll just say, forget about the internal resistance. But if it's not, we have to consider it. And so it's one more resistor in our circuit. Here's the good news, is we don't have to do anything different than we've been talking about for the last hour. We'll treat our resistor just like it's just another resistor into the circuit. Now that's going to make it harder because now there's one more resistor in the whole thing, but nonetheless, if we can ignore it, that's better, but if we don't, we know how to handle it. It's why your author kind of does this little picture here, and he actually then shows kind of the sulfuric acid and the lead oxide plates, and so this is, exactly, our picture here. Here's our battery and our sulfuric acid, and saying, all right, that's our chemical reaction. And he spends a little more time in the next picture talking a little bit more about the chemical reaction. But here's what this would mean. And so notice then he uses this word load and internal resistance, and he just applies the loop. He says, all right, let's do a loop here. Where do you want to start? Maybe I'll start down here. Maybe I'll go clockwise. And if I go from here to here, remember we need to pick a direction for the current. It's a single loop, so let me not call it current 1 or current 2 or current 3. Let me just call it the current. And so if I went from here to here, I would say the change in energy is IR. And I'm going to go back 45 minutes and ask you, okay, would it be a plus or a minus? Well, if the current's going this way, I'm going with the currents. So just like me hiking in a creek, splash, splash, splash. If I'm walking in the creek and I'm walking in the direction of the flow, it's a minus. Then I get to this EMF, and I go from little bar to big bar, so that's a plus script E. Of course, the two of these together is what I was saying earlier. This is the terminal voltage. Then I go around the loop, and I would go I capital R. Now, before I ask you about plus or minus, let me just remind you, remember this is a single branch, so I could argue because of conservation of charge that whatever current comes out of this battery has to go to that resistor. That's why I did not call it a current 1 and a current 2. It's just the current. This is just one loop. There's no nodes here in this simple one. But I am going with the current, so I'd put a minus. I would then complete the loop, so I'd put a 0. And if the question then said, what is the current? I guess I would solve it like this. I would put the script E on this side. I would then move both terms that are negative to the other side. I would then factor out the I. I would then notice that these two are in series. I can get the equivalent of those. Or maybe not even pay attention to the fact that they're in series. Just put current I equals to EMF over capital R times or plus little r. And so that would be the current in this circuit, and that's exactly what he did right here. He said, okay, how much current would be flowing in this circuit now that we included the internal resistance of the battery. So, like I said, it's nice to keep track of that. In fact, I set up a little demonstration here to show you and said, all right, if I took a voltmeter and so this will give me a chance to show you hooking up a voltmeter. Notice that I am going to then measure the energy. And so the big thing I want to say is voltmeters we hook up in parallel with whatever it is we're trying to measure. Because what happens is a voltmeter measures the energy. And so what happens is you take a little wire and you measure the energy up here and you compare it to the energy down here. And so you want to measure in parallel. All right, so let me disconnect this jumbled mess. Actually, I'll disconnect that on the break. It's about time for our break. But I'll hook up then my battery. So here's your standard Duracell D battery. Should be about a little more than what we call 1.5 volts. And so let me set my little meter. Remember, I had it before as an ohm meter. Let me move it where it says V with the bar. That's a DC voltage. And I'm going to then plug it in to my battery. Notice parallel. I'm going from the plus and minus terminals. And if I read this, whoops. And other than I have a negative, which is just which one's bigger. The way the meter works is it always takes this connection and subtracts it from the lower one. So if you hook it backwards, you get a negative. If you're just trying to get the number, it doesn't really matter. So I could have ignored it. But I didn't want to confuse you, so I'm just going to say here, it says 1.55. Okay? And so what that means here is I am reading the voltage on the terminal, and I would even say right now I haven't hooked anything up. I don't have a load hooked up. And so my current is 0. And so in this configuration right here, my terminal voltage is actually the EMF. And so this is telling me how much voltage am I getting from the chemical inside. Okay, and it's an alkali battery. I don't know which ones they use, but so it's obviously some alkalis in there. And so, okay, I have a voltage of 1.55. That's the typical number we get from a Duracell alkali battery. Okay, now let me hook up a load. Okay, so I will disconnect that. It's not a very exciting load here, but you saw this resistor last time. Here's this long wire that's wrapped around here. You might remember it slides across the top, so I can kind of touch the wire anywhere in between, so I can change the amount of resistance. At this point, I'll just start with it on the far end and say, all right, let me hook up my little circuit. So I'm going to go from my battery to my resistor. It'll go through all these wires, then back up to this shaft, and then return back to my negative. So I would say now I actually have something flowing. And so I would say, well, what voltage do I get now? And I would say it must be V minus IR. Now, hopefully, it's not much. Let's see. See, it's now at 1.50. And so I would say that right here, this term right there was worth 0.05. It dropped it down. And so notice that depends upon how much current and how much resistance is in my battery. And to prove that to you, watch this last step before we take our break here, is what if I lower this resistance to my load? Doesn't this say I'd get more current? And so I'm going to make this resistance less, which is going to make more current come out of my battery. And because more current comes out of my battery, my terminal voltage is going to go down. And so, let's see, I'll just kind of move my little forward here. And so there's less resistance to my load. That means more current is coming out of my battery, which, as a consequence of that, I get less voltage from my battery. Now, not less from the chemical reaction, but less total from the battery because of the internal resistance. And so as I make more and more current the terminal voltage goes down and down and down and down, and I don't want to overdo it, so I will stop there and say it's a great time for a break here. So let's take our 15-minute break and come back at, 10 till. And we will. Hey, welcome back from our break. Let's get started. And we ended up talking about terminal voltage, and I was kind of showing a setup. Let me go ahead now and do an example here. And so I wrote, or two examples actually. We'd be in a good spot, but one of them was for the terminal voltage. I forget which number it is I wrote down. What is it? So we did number 2. Let's do 17. And so 17 is one of these ones that hopefully now makes sense given what I just did with the terminal voltage. But the equation we have is right here. And I'll just say it again, we get a certain amount of energy from the chemical reaction, but we lose a certain amount of energy because we got to get it out of the battery. And so what we have for the terminals, what we have left to drive our load, what we have left to start our car. In fact, maybe that's a good example. It takes so much current to start a car that you'll often see the light. Oh, I wanted to keep those. I think that was 105. I'll remeasure it. But you'll often see the lights dim a little bit, maybe even a lot, when you go to start it, because it is the EMF minus whatever that number is, and it can be a lot of current while you're starting your car. Number 17 isn't quite that big, but it says here, what is the terminal voltage of a large, and maybe should I make this a little bigger? Yeah. What is the terminal voltage of a large 1.54 volt carbon zinc dry cell used in the physics lab to supply 2 amps to a circuit if the cell's internal resistance is 0.1? So going from the words they have, it looks like they're saying, okay, we have a EMF of 1.54 volts. And then there is some internal resistance that is hopefully small. This is small, but even bigger than we probably would like it for a battery to be. But there is some loss of energy then to come out. And we're using this to run a load. And there's where they just use kind of that general word, a load. They don't really say what they're operating. So I'm just going to say it comes over to here, and then we have this, I'll call it R for load. And I'll just say it's a light bulb since I don't know what it is. But I do know this, that whatever the resistor is, it's allowing 2 amps to flow through. Okay? And actually, that alone is enough to just solve this problem, because they say, well, what is the terminal voltage? I'd like to put a little T. Well, again, conservation of energy says it would be the script E minus a little bit of loss, and our script E is that 1.54. So this is 1.54 volts, and then minus, and it looks like I've got 2 amps multiplied by 1/10 of an ohm. And let me do that in 2 steps so that I can actually write out this number. But I guess a 2 times a 1 is 0.2. But what I want you to see and remind you, an ohm from last chapter is how much voltage do you need per amp. And so an ohm is a volt per amp. See, that way the amp here will cancel with the amp here, and your units will be a volt, as they should. Since we are taking a volt, we got to subtract the same units. So this should be 1.34 volts for the answer. So pretty close to a plug-in and chug type of problem. I'm going to take one more step for this problem, even though it's not asked, and say, could you tell me then what the resistance is of the load in order to get this current based upon what is described here? Now, I say that's one more step, but I think we have to do that anyways, because look at the next part of this question. B says, how much electrical power does the cell produce? Well, I guess it's part C, we're going to need to do that. See, how much power goes to the load? So they begin to ask something about the load. So maybe before I get to C, let's go ahead and do then B. I'll keep this little analysis. I'll erase the circuit, but I'll keep the numerical analysis of the loop. So I guess I'll get rid of this. But I think I'm going to want to use this as we solve that problem here. All right, so this gives us a chance to go back a chapter and remember that power is current times voltage. And that was the question in B. Let me read it again. How much power, right there, how much electrical power does the cell produce? Now, I think what the author is saying, there could be some confusion here, but I think he's focusing on this part of it. How much is produced? Some of it is lost coming out of the battery, and some of it is delivered to the load. And because of conservation of energy, of course, those two that are being consumed by the circuit are delivered by that chemical reaction. So in terms of how much energy is being, or power I should say, so the rate of energy is being delivered, I know that we've got 2 amps in currents coming out of this battery. That was given in the problem. And the voltage, well, that's what's produced by the chemical reaction. And I guess this is a carbon and zinc chemical reaction. So as we get our zinc carbide, we're going to then have this equation. So let's see, if I double that, that's an 8 and that's a 3. Okay. And let's just check our units here. It is asking for power, so by unit analysis, this should come out to be a watt. And so let me remember that an amp is a coulomb per second. Coulomb per second. And a volt is a joule per coulomb. So coulombs will cancel off and we will be left with joules per second, and that's our definition of a watt. So I would say that under these circumstances our cell is delivering about 3 watts. 3.08 watts of power is being generated, or you might say converted from a chemical energy into an electrical energy. And then where does it go? Well, it gets delivered in the circuit. So if this is a necessary reality of it, this is what we hope wasn't there, but it looks like some of the power or some of the energy would go here, so the battery would start to warm up. This would show up as heat. And this would be, say, a light bulb, so some of it would show up as heat and some of it would show up as light. Obviously, our goal is to make the light, but we've got to have heat along the way, just the natural consequence of it, and less heat the better, but we really want light out of this. And so that's our goal here, which I think brings us to part C, which gives me 2 directions I can go with this. Part C is saying, what is the power going to the load? Now, for the load, there's a couple ways I could do this. Maybe I will do just the simple current times the voltage. And probably the easiest way, but maybe not the most kind of obvious way, but I'll do the easiest way first, is to say, well, how much current do I have in my load? Well, that one's easy. That's the 2 amps. Because they made it very clear that the 2 amps comes out of the battery. So it's just a single loop, and because of conservation of charge, the current of 2 amps got to go through the load, it's got to go through the internal resistor, and it's got to go through this cell. It's got to go through the chemical reaction. So that's all 2 amps. So just like I had 2 amps in the cell, I have 2 amps in the load resistor. Okay, but how much voltage do I have? Well, I would be tempted to go over here and go find out the current and multiply it by R. So I'd have to find R. I already have the current. And I think I will go that way because, like I said, that's a fun direction, but I'm going to hold off on that because I'm going to take this conservation of energy. Remember I said if you started down here, call it point A, and if you went around the whole loop, it would add up to 0. That was the same way of saying that if you call this point B, if somebody goes on a hike and there's, say, 2 friends, they drive together, they get out of the car together, and one friend says, I'm going to hike this trail, you hike the other trail, we'll meet up at the top. So the person who goes from A to B this direction is going to increase the same height that the person who goes up this trail does. And we already know this one, right? This is the terminal voltage. This is what we did in part A. And so without any extra work for my load resistor, I would have to say, since the person who goes this way goes up by 1.34, means the other person would have to go up by 1.34. Or if you want to think of the whole loop having to add to 0, you would say this person goes up 1.34, so if they continued on, they would have to go down 1.34. Either way you want to look at it, I know the voltage on the load is 1.34. Notice it is not 1.54, right? Some of that energy, some of that loss of energy, the consumption of energy is in the internal resistance of that battery. So, like I said, this is probably the easiest way to calculate it. And so this would be 2 times 1.3, oh, I guess I don't need a calculator for that. 2.68 watts. And then again, notice that this number is lower than in part B. Part B, this was the energy being delivered by the chemical reaction, and this is what is being, I guess I should say generated. This is what's being generated by the chemical reaction. This is what is then being delivered to the load, and the difference between that would be how much is on here, which isn't part of our question, but I thought it might be nice to look at. So is this 0.40 watts? Is that what that comes out to be? So if I take that and subtract that. And so if there was a part D, that would be a good question. How much energy is being consumed internally? So how much is this battery warming up? And maybe even in danger of catching on fire if this is not designed well and have too much heat. Now, as we said earlier, you could just apply Kirchhoff's laws at the beginning and go around this whole loop and figure out then what the internal resistance is. So if there was a part E, that would be a good question too. Find the load resistance, since you know the other ones. So the EMF is 1.54 volts. The load resistance would be a good question to be asking for. The internal resistance is the 0.100, and the current is the 2 amps. And so if I go 1.54 and bring this over, this becomes a 2 times an R plus a 0.2. And so now I can solve for R. And so 1.54 minus 0.2, 1.34, and then divide by 2 is 0.67 ohms. And like I said, I know they didn't actually ask all these ones, but it looked like a good problem to not only do what they asked, but maybe expand it. And then to finish up, if you wanted, you could say, wouldn't power on the load resistance be I squared R? Now, we don't need to actually do that because we already answered C, what is the power? But this was kind of my gut feeling at the beginning, just going back to taking the current and squaring it and times the load resistance. But to do that, you had to solve for the load resistance. So that was kind of my first gut reaction to do that in C. And it was kind of a long way, so I go, well, let's do it a different way. Let's do it the short way first. But like I said, my gut way was to say, hey, it's current squared. They gave us, all we got to do is do this calculation that we did before the break, or this formula before the break, and we'd get the resistance. So I'll take a 2 and I'll square it for the current, and then I'll take the load resistor of 0.67, and I get 2.68 watts, which sure enough, not a surprise, matches what we got in part C. How much do we have here? So there's a good one. Again, doing some more circuitry, a little more complex, involving a battery with an internal resistance. But let me clear the board now for a little harder one here. Let's try one that I would put in the realm of the grand finale here. Because if this one makes sense to you, then I think you'll be doing well in this chapter, because I don't think they get really any harder than what we're about to do. Now, there is an exception, I suppose. I haven't really talked about capacitors yet being in the circuit, but that's coming up here real soon, and that's how we'll wrap up the chapter here. But my next one was number 39. Looked like a good one. It says, go ahead and solve example 21.5, but go ahead and use this loop instead of the one they did, and show your steps. So let me kind of merge all those together, which loop they asked us to do, which one did they do. But let's look at the circuit itself. And so the circuit's pretty advanced. Looks like it's got 3 branches. So each branch has its own current, so there's 3 currents. We've got 2 batteries. Each battery has its own internal resistance. Then we've got 3 other, what I'll call load resistors, R1, R2, and R3. And so we got to hook this crazy thing up. Now, I'm just going to say I'm going to make one modification. And that is, let me hook this up with numbers that I actually have. So I can hook them up, we can do calculations, and we can measure things. That way we can see how to measure, and we can check our math and see if it matches reality here. So I'm going to come over here and say, all right, looks like we've got a battery and another battery and a load resistor down the center, an internal resistance, another resistor, another resistor, and another internal resistance. And if I remember the notation, they called this middle one R1, they called this one R2, they called this one R3. Then I think the top one is what they label number 1, so they call this EMF1 up here. EMF1 and little r1. So this right here is the power supply, or the battery, or one of them. Because then we have another one right here, which they label as EMF2 and little r number 2. So that gives us a total really of 5 resistors, and it also hopefully illustrates my point here that what we're going to do is take advantage of our conservation of energy, conservation of charge. We'll look for series, we'll look for parallel, we'll just treat our resistors, internal resistors, as part of the overall circuit, and we will just go through and write out our system of equations. And it looks like there's probably going to be needing 3 equations because all 3 unknowns, right? It solves for each of the currents. Okay. Now, like I said, maybe the 2 things I'll change, and so I hooked up 2 power supplies. This one was already hooked up before the break, and then during the break I grabbed a second one here, and so let's just do a 6 and a 3. All right, they have a 45 and an 18, but I just go, well, change the numbers a little bit, but a 6 and a 3. So let me come down here and say, all right, so E2 I will set to 6 volts. And E1 I will set to 3, and that one was a little more unstable, so I think it was like a 3, the meter on top says 301, but I think I was getting a 302. No, 2.998. Let me call that 30. Okay, I'll go with that. So to three significant figures, this is 3.0 volts. Okay. And let me use those resistors I was using before, but let me relabel them. Because this small one, let me call that one R1. And that's the one I erased. It was 105 something. So let me come back over here and say, all right, what was this thing? And just to get us going again, it's 105 point something. 105.2. Oh, whoa. Connections are a little loose. Don't like that. But see if the meters match, huh? Oh, yeah, okay, that was 105.7, wasn't it? 105.8, something like that? Oh, you guys probably have it in your notes.
Yeah, it was 105.7.
Okay, so I must have used this meter. Okay, let me just call it 105.7. So I'll take a small one here. So 105.7, okay. And let me get another small resistor, R2. And I'm going to grab the small one that is on one of these other boards here. Okay, and so I don't mix these two, but this is roughly the same. These are our laboratory equipment, so I bet it's 105. Okay, so 105.4. All right, so I'm going to use those as my two small resistors. Then, as my bigger ones, R1, R2, and R3, let me use the ones we measured earlier in the class. So that would be this second one and the third one. So let me call the second one here 205.7 and the third one 751. And these are, of course, all ohms. And the one that I took away, let me replace it with the one that's still on this board, but just above it, so it's a little higher. I think it's in like the 3,000 range. I don't like how loose that wire is. Doesn't make a good connection. Okay. All right, so let me see what our new one's going to be here. All right, so we've got 3005. So 3005 ohms. All right. So let's work this problem, but use these numbers and see what we get. And I have a feeling that this is going to take, like the grand finale of the homework, a lot of space to kind of write all these out, to think it through, to get some numbers. All right, so let me begin by remembering the general principle: conservation of energy, conservation of charge. Let me look to see, is there anything that can be simplified? Is there anything that has, and I like to start with series, because I think series are a little easier than parallel. Is there anything that, you know, one flows into another, that has the same currents? And maybe I should label currents. In fact, now that I got rid of the overhead, I should use the same labeling he does, but he calls down the middle 1, and so I will too. So he says, let's call the current this way 1. And by the way, this is a good time for me to remind you, it doesn't matter which way the current actually is going. This is just a labeling. If we solve it and get a negative number, that just means we labeled it wrong, and it was actually going the other way. So But we do need to label it because remember, when we go plus or minus, we have to know, are we going around the loop with the current or against the current? So we got to have to label it. So that's step one. Then it's going to hit this node, and your author calls this number 2, and this going down here number 3. Okay? Now, I'm hoping you'll see from the very beginning of today's lecture that current number 2 would be the same all the way through this upper branch. And current number 3 would be the same all the way down this lower branch. So 2 and 3 come together right here and make 1. Okay, so if you look at this node or this node, you're going to get the same thing. So we don't want to look at both nodes. We only want to look at one node. And so I would say my first equation is to say that current 1 equals current 2 plus current 3. That's what I get in the green. All right, now, you'll see it if I write out the equation, but hopefully you already see it. Don't we really have this resistor and this resistor in series? Now those might be harder to see because we've got a battery in between, but if I didn't have the battery, wouldn't it flow from that one into that one? But see, remember, the only requirement for series was that they flowed one right into another, and you could have a whole series of 3 of them. And so even though we only looked at 2 and said we can combine them, as long as they're in that same branch, you would say that these two have the same current. And you can combine them together. And so I could save myself a little bit of work and just call that one resistor. But I'll pretend I don't even notice that at first and just write out the equation of the loop. So let me start here and go around the loop. And I'll do the top loop. So from here to here would be current 2 times resistance 2. And since I'm going with the current, I would put a negative. So there's our conservation of energy. I'm going to add around to the loop. Then I would get to this EMF, which I'm going to call E1. And I'm going from the little line to the big line. And so as I go from the little line to the big line, that means an increase. Okay? And so this is a good place to kind of remind you, we did about an hour ago, there's one way of calculating the voltage from a resistor. It's right here. There's another way of calculating it from a battery. And don't mix the two. Batteries, I think, are a little easier. You just write whatever number's there, and then you look whether it's a plus or minus from the big line to the little line. The current is important for the resistors. And so it's just IR. Now, if I keep going, I'm going with the current. So this would be a minus, because I'm going with the current. This would be current number 2, and this would be little r1. And then finally, as I complete this top loop and I come around, I would say right here I have then a current 1 and a resistor 1. And I guess I already put the negative in there, but I'm going with the current number 1 as I return back, and that completes the loop, so that's a 0. Now, if you didn't notice, this R2 and little r1 are actually in series, you might see it right here when you combine them together and say, hey, this one and this one each have an I2 in it. And if you factor that out, that means you can just add them together. That is the equivalent right there. And so that's why I was saying that's how we derive the special case that they're in series. So you could have saved yourself a little bit of effort by recognizing that, hey, those are in series. However, that's not that big of a step. And the same thing would happen down here, but sadly that's all we can do. So let me go down here to this bottom loop and do the same thing. And just to maybe mix it up, I'll change colors so we can see that we have different sets of equation. Oh, by the way, this is a good time maybe to remind you that we're trying to solve for three unknowns: current 1, current 2, current 3. So we need three equations. Three equations solves three unknowns, right? One equation for one unknown, two equations for two unknowns, three equations for three unknowns. But they have to be independent ones. So obviously these are not three independent ones. This is just a simplification of that one. So I can use one of these, but not both of them. In fact, I'll just cross this one out because I'm going to use the simpler one of the two. Okay? Likewise, as I said earlier, you would not want to do the top loop, the bottom loop, and the big loop and call those three equations, because the big loop is nothing more than the sum of the top and the bottom. And so my answer to you was to make sure you do as many loops as you have small loops. So we have two small loops, and I'm actually going to do both small loops. So I'm going to do the two small loops and then the node, and that's going to be my three equations. Okay? So let me do this bottom one, and so maybe I'll just kind of do the same thing. I'll start down in this lower left-hand corner, and I'll go around clockwise. So when I go from here to here, right here, this one right here, this equation would be, let's see, where should I write it? Maybe I'll just put it here. So this would be current 1 times R1, and since I'm going against the current, I would go uphill. And so again, imagine yourself walking in the circuit itself or in the creek, and you're going against the current. Okay? And then I'll say it again. This is where it can get confusing. It's like, okay, there's two things moving. There's you moving around the loop, and then there's the water moving, right? There's the current. All right. But I'm moving clockwise, and I'm going against the current right here. So it's a plus. Then I get to this R3, and I'm going to actually save myself a little bit of work and just add those two together, because our same logic up here, I would say those two are in series. And so I would be going against current number 3. And because it's against current number 3, it's a minus sign. It's current number 3, and then I would say it is R3 plus little r2. And so that would incorporate both of these. And that saved me a little bit of work, but certainly not much. Okay. But the big one is right here. Here is voltage number 2, and I'm going from little bar to big bar, so that's minus E2 equals 0, and then I return. So that's where we started the lecture. We started the lecture with the general principle. Conservation of energy for each loop, and conservation of charge. And really that's as much simplification as we can do. Now we're left to solve the algebra. Okay, so let me put in my numbers and work from there. For the green one, there's nothing I can put in quite yet. Okay, so let me come over here and put in what I can. E1 is the 3 volts. So I'm going to put a 3 volts here. I'm going to move this over, and right here, number 1, I'll put in R1, so that's 3005. So 3005 times current number 1. And then over here, I'm going to add these two together. So R2, let me just add them real quick here. R2 and R1, 1057. So 1411, 311.4. All right, so this is 311.4. I'll put a minus, and there's current number 2. All right, so I would call that the simplification, if you will, of the top loop. Let's put in these numbers here, and maybe just to make it match, I'll do it in red. Let me put in equals. Let me move then this one. Did I do this one wrong? I think I did. Then I going a little too fast. I went from here to here. That would be against the current. And then here to here. Oh, I'm going against the current. Okay. So against the current means I'd go uphill. You saw that, right? You just tested me. Okay, good. So going against the current. All right, so I'm going to move the E2 to the other side. So E2 is 6.00 volts. Okay. And then, of course, I still have this number here. This is this 3005 current 1. And then plus, and so this will be current 3. And I need to add these two together. And so number 3, which is the 751, and R2, which is the 105.4. 4, 6, 5, 8. So 856. So 856.4. All right. So I'll say it again. I got 3 equations, 3 unknowns. Right? And the physics part of this, I hope I've accomplished. Right? I've written out the equations. And now it's a matter of mathematics. So that's still kind of hard. But I'm going to kind of trust that you've remember some of your algebra here. Obviously, you wouldn't have come this far if you haven't been relying on some of your algebra here. So let me go ahead and solve this. I'm a little worried about time because I want to show you the capacitors real well. Shoot. Well, maybe I'll just go quickly here, huh? All right, so I guess the first thing I would do is I'd leave the 3 here, set it equal. Maybe I will put this in here and say, well, you know what I'll do? Let's set it up to solve, and if we have time to completely solve it, I will. But at least let me help you set it up, and then I think you can do the rest. Then I'll show you the capacitors, and if there's still time. So let me do the next line here. So I would say 3005, and then I1 plus, I1 is number 2 plus number 3 minus 311.4 I2. Because as you can see here in the next step, I would have 3005 minus 311.4, making 2,694 I2 plus 3,005 I3 equals 3. So that's what I would get by substituting in and getting rid of I1. And likewise, the same thing here. I would have 3005, and I1 would be I2 plus I3 plus 856.4 I3 equals A6. And so if I take the 3005 and add 856.4, I'm going to get 3,861.4 I2 plus 3,005 I3 equals 6. And so that's the first step, and a big step, because now notice, by taking this first equation and substituting it in, I now have 2 equations and 2 unknowns. All right, and so my next step would be, and hopefully I'll still have time, is to solve this for I2 and put it into here. And then I will only have an I3, because I will solve for I2, which will have an I3 in it. I'll put it into here, and I'll have one big equation that has only I3s in it, and I can solve it. And like I said, this is the grand finale. So hopefully I won't run out of time completely, but I do want to then show you the last bit of physics here. Before we run shy, is what would happen if you did this? what if you took a capacitor and you charge it up? And so let me go back 2 chapters to our chapter where we're introduced to the capacitor. Let me actually charge it up like you saw last time. So here is my capacitor. Here is my 6 volts power supply. Here I will start charging it up. All right, so I'll give it a chance to charge up. And once it charges up, I am going to then connect it to a resistor. And so this would be our circuit diagram. And so what's going to happen is the current's going to flow. And here would be my question, like we've been doing this whole chapter, could you solve for the current? And you can see that this one gets a little more complicated, because what you would have is you would have, of course, 6 volts at first, but then as the charge came off the capacitor, you have less voltage. Maybe I should put that back on the board here. Remember, capacitance is charge over the voltage, or so voltage equals charge over the capacitance. So at first, you would have 6 volts. And so if I made a graph here of time, I would say I might get a lot of current at first. I first took this up. But once the current starts flowing, now you have less charge on your capacitor. Less charge means less voltage. So maybe now it goes down to 5 volts. Well, if it goes down to 5 volts, that means less current. And so you're going to get a decrease. Now, the current's still coming off. So, or I should say the charge is coming off, making the current, and so now it goes down to 4 volts. So you get even less current. Well, more charge comes off, so you get down to 3 volts, and you get less and 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 less. And so I would suspect that the current as a function of time probably looks something kind of complicated like this. And of course, I didn't solve this for you 2 chapters ago, but I did connect it up. I said, let's grab that light bulb. And so let's then actually take a capacitor. Let's hook it up to our light bulb, and let's watch, at least visually, the current. And so at first the current was pretty high. And then as time goes on, it decays away. And what we're going to see here, if we solve the math, is it is an exponential decay. And so let me try to write out the equation here. This is why this one was done last, because there's some calculus involved. I guess I would do this. I would say the same physics we've been doing the whole chapter, let's just add up around the loop. See, around the loop, you would go from here to here is the voltage on the capacitor. I'll put V sub C. Now, this is the first time we've had a capacitor in our circuit, so let me just write it as V sub C for right now. But then as I go around the loop, there would be a decrease in energy, IR. And I say decrease because we're going with the current, so there's the minus, and then I get a 0. Now, if I come over here and remind ourselves that the voltage is related to the charge on the capacitor, I would say this is a Q over AC equals 2 minus IR equals 0. Okay, now here's where we'll need a little time for the math also. But I would say something to this effect. I'll leave these equations just in the unlikely event we got enough time to finish the math. But if I write this, maybe I'll put it right here at first, as Q over C minus, and then let me write this as dQ over dt R. So I'm going to go back a chapter. Remember I said there's nothing new physics in this chapter, but it is putting together last chapter and the chapter before that and the chapter before that. So putting all three of these chapters together, this is how I would just say the current is. Now, this is hopefully going to make sense to you. I would got to be careful with these Q. Isn't this the Q on the capacitor, but this is the Q that goes through the resistor? Okay, now, again, let's use conservation of charge. If there is a delta Q on the capacitor, in other words, what comes off of the capacitor goes into the resistor. Except one loses and one gains. So I'm going to say this. I'm going to put a little R down here to say this is the charge that goes into the resistor, but I'm also going to say this, that the delta Q on the capacitor is equal to negative of the delta Q of the resistor. And that's our conservation of charge. So I told you the capacitor is a little tricky here, but it does hopefully make sense. So if I do this, if I put Q and I be specific here, this is the Q on the capacitor divided by C. And then I change this from the charge that's going into the resistor to what is on the capacitor. I will have to change the sign because the dq is negative. Now, if you let me take one more step here with a little bit of calculus, and that's really what I want to do, is I want to do the calculus with you, kind of like we did with the conservation of energy, so that let's get the answer. So you don't have to do the calculus on the homework or on the test. We're going to get the results here. I'm going to say in the limit of a short period of time, this is actually a dq dt r 0. And now I hope you see where I'm going with this, is I now have an equation for the charge on the capacitor. It's a differential equation. And so I'm going to have to solve a derivative, but that's cool. Remember, we said we can separate the variables and then integrate? And we've done that a few times. So let's give this a try. So I will put Q of the capacitor over R. I'll move this to the other side, minus. I'll even bring the R in front of the derivative. Oh, sorry. It might be nice to group my constants together, and it doesn't really matter which side you want. You can put it on the right-hand side, the left-hand side. I'll put them over here. So I'll put the negative over here, and then I'll put an RC, and then I'll put a dq over a dt. And that's why I was saying, solving this is a little hard. Hopefully the physics is easy. The physics is the easy step, right? We just add it up around the loop, conservation of energy. We just did conservation of charge to figure out the connection between them. So using conservation of energy, conservation of charge, we have a differential equation, which now we have to solve. But as I said, you can solve these by separating them. And so everything with time, I'll put on the left, and everything with charge, I will put on the right. And let me just drop the C now, just so I don't have to keep messing with it. This is the charge on the capacitor, and the equal and negative of that is the charge that goes through the resistor. So let me just remind myself of that. But I'm just going to have a hard time solving this for Q. But see, now I can integrate. I've got them separated. So let's do this. Let's say that we want to watch this capacitor discharge. So we'll start at 0 time, which means the capacitor starts with some initial charge. Remember, I started this up with an initial charge? So let's call it Q naught. And then after a period of time, so we'll call it T, it's going to have a charge Q left on it. And so let's solve that. This one's pretty easy because it just becomes a minus 1 over RC, and then you get T evaluated from 0 to T. And so that constants pull out, and you just have the integral of dt. That's just T. This is that harder one that we've seen a few times. This is the one you guys told me before. It's the natural log. So this would be the natural log of Q evaluated from Q naught to some value Q. So this would be ln of Q minus ln of Q naught. But like we saw back in Physics 110 when we came across these, is we can write that subtraction of exponent, or subtraction of log functions as a quotient. Then it might be nice to get rid of that natural log by exponentiating both sides. So this would become e to the minus t over rc. And this side would then become q over q naught. And finally, the grand answer of all of this is to say that the charge will follow an exponential decay. It fits exactly kind of what our gut was telling us earlier on as we said how the current is going to flow. Now, technically I didn't solve for current. Technically I solved for charge. However, if I make the next step and just remind you that the currents in the resistor would be equal to how the current changes with time. Well, maybe I should say in the resistor, which is negative how it comes off of the capacitor. So I'm going to go ahead and then take the derivative of this. So the derivative of this, I guess, would be the initial charge. And fortunately, derivatives of exponentials are pretty easy. They just get you another exponential. But then the chain rule gives us a negative 1 over RC. Okay. Which, when we simplify, the negatives go away, and we get the original charge over C times R, e to the minus RC. So I'll even simplify this a little, but I want you to see that it's that same exponential decay right here. And so the charge decays away with this time constant, which we're going to call it a time constant. We'll call it the RC time constant. And the current has the same thing. In fact, we'll just call this initial stuff right here the initial current. And so to be a little more accurate to say I want to solve this for current, like I said, I actually solve for charge, so I need to take the derivative of that to get current. But this would be then the answer to say, all right, here's the currents in a capacitor. And so it would start with some initial value, and it would decay away, and it would follow a pattern that is proportional to this 1 over RC. So you can see that what we call the time constant, the time factor, is this resistance times the capacitance. And so another useful example of a capacitor, remember we were introduced to them and I said, hey, the simplest thing of a capacitor is just an energy storage device. And so we stored it up and we saw that it stored right here, and we ran the light bulb for 15 seconds or something. And so one usefulness of a capacitor is that it stores energy. But today I'm hopefully showing you a second useful idea of a capacitor. And the idea of the capacitor is it's a timing device. And how long does it take to charge, or how long does it take to discharge, is an important question. And you can use that as part of your circuitry. Your author gives you many examples. I'll just pick on one since we're short on time, but one of them is how does the turn signal on your car work? Or how does the dome light on your car work? You probably have noticed that you get out of the car, you shut the door, and the dome light stays on for a while, and then it shuts off. There's a timing device. If you turn on the blinker, you driving along, you turn on the turn signal, and then it blinks, pause, blinks, pause, blinks, pause. But there's a certain timing to that. And the electrical engineers have designed it based upon how long does it take for a capacitor and a resistor to either discharge or to charge. And so this is that RC time constant. Now, sadly, I did not give myself enough time to do the reverse. Let me leave this picture on the board. Let me not try to solve the mathematics, only to say the mathematics is essentially the same. What do you get if you charge a capacitor? So the circuit's a little more complicated because you have to have a battery through a resistor, through a capacitor, and then back. And so what will happen is the current will begin to flow. If we write out our equation and call this V, call this R, and call this C, you would eventually beginning to get positive charges on here and negative here. And so your equation would look like this, V, and then minus IR, because I'm going to add up around the loop. So starting here, I'd go V, then I'd go minus IR. Then right here, I would go from the plus to the minus on the capacitor. So this would be a minus, and the voltage on the capacitor is the charge divided by its capacitance equals 0. I think you can kind of see that this equation looks a lot like the one we just solved. The only difference, it has a V in it now. Last time we just had these two terms. Now we have this term. But interestingly enough, as your author points out, and like I said, I'm going to be out of time to actually solve it, you will still get this initial burst of time, or initial burst of current. And as the capacitor begins to fill up, it blocks more current, or it opposes it. You have to remember that it would look something like this. If this was 6 volts, at first there'd be no charges on here, so no voltage here, and so there would have to be 6 volts here, so there'd be a lot of current, because these two together have to add up to that one. A moment later, this is going to build up enough charge, maybe worth 1 volt, so this would only now be worth 5 volts. That's why there'd be less current. A moment after that, this would be 2 volts, and so this would have to add up to 4. And then this would be 3, and that would be 3, and then that'd be a 4, and that'd be a 2, and this would be then a 5, and this would be a 1, and then finally it would get full. This would be 6, and that would be 0. And so you would still have this current that would exponentially decay. And so again, you can write this as a differential equation and solve it. And kind of glad we don't have time. I don't know if the work is worth it. It's actually the same math we just did, and what I want you to see is the end product. And so the end product is whether you are charging or discharging a capacitor, it follows this exponential decay. And what's called the time constant, how long does it take to charge or to discharge, is dependent on both the capacitance and the resistance. And since I'm out of time, I won't actually calculate this last one, number 63, but let's read it together, because you'll see it is a pretty much plug and chug type of problem now that we've done the majority of the work here. It says, a timing device in an automobile's intermittent wiper system. So there's another example. If you ever have your wipers and you put it on the intermittent setting, you've got a little knob and you can adjust the resistance. And that's a timing device. And it says, okay, wipe. And then the wipers just sit there for a while until that capacitor either charges or discharges, and then it goes wipe again. Okay, and so how much time does it take depends upon those two factors, R and C multiplied together. So if we wanted to make a timing device and we wanted to make it variable so that the operator can adjust it, we'll make a variable resistor. And it says here, we want a time constant that utilizes a 0.5 microfarad capacitor as a variable resistor. And over what range should R be so that it varies from 2 seconds to 15 seconds. So in other words, we would want RC to equal 2 seconds for the first resistor. And for the second resistor, we want it to be a 15-second interval. And so we've got the 2, and we put in the capacitor of a 0.5 microfarad. We can find out what R has to be. So that would be the smallest resistor. Then as we turn the dial, we can get to the biggest resistance, and then find out how it changes the rate at which our wipers work. All right, well, sorry I couldn't plug in the numbers for those last couple of ones, but hopefully they were enough to at least get you started, and enough that then the video solutions I make will help. All right, we're done. I guess we're done with the chapter. We're done for the day. Let's call it quits so the other class can get in here, and we will go to lab and see you guys at 11:10.